Alright guys, in this video we're talking about section 3.4, the binomial probability distribution. Now, first of all, let's take a look at the definition of binomial experiment. An experiment for which conditions 1 through 4 are satisfied is called a binomial experiment. So, if we want to identify if an experiment is a binomial experiment, we just need to check if those four conditions are satisfied or not. Number one, the experiment consists of a sequence of n smaller experiments called trials, where n is fixed in advance of the experiment. So, the number of trials of a binomial experiment should be fixed in advance. Okay, that's number one. Number two, each trial can result in one of the same two possible outcomes, which we generally denote by success and failure, which means each trial of an experiment should have only two possible outcomes, success and failure, or yes or no, or head or tail, whatever. But anyway, there gotta be only two possible outcomes from each trial. Number three, the trials are independent, so that the outcome on any particular trial does not influence the outcome on any other trial. So the number three is independence. Number four, the probability of success, P of S, is constant from trial to trial. We denote this probability by P. So if the probability of success is P, then the probability of a failure is going to be equal to 1 minus P. Okay? All right, so once we know the conditions of the binomial experiment, let's take a look at the example here. We got three examples, and we want to see, we got to check if they are binomial experiments or not. Let's see, number one. So if we want to identify if this is a binomial experiment or not, we just need to check if all those four conditions are satisfied or not. Let's do it one by one. Let's say condition one. If the number of trials fixed in advance. In this case, I don't think so, because this example doesn't mention anything about the number of trials will be conducted. Okay, so the condition one is violated, so this case is not binomial experiment. Okay, this is not a binomial experiment. But let's just take a look at if any other conditions satisfied or not. Condition two. Each trial can result in one of the same two possible outcomes. Yeah, I think this one is satisfied, because if we toss a coin, there are only two possible outcomes. They are head and tail. So number two is satisfied. Number three, independence. If trials are independent of each other, I think so, because whatever we get from the first toss will not affect the result of the second toss or any other tosses. So the condition three is satisfied. Number four, the probability of success is constant from trial to trial. We denote this probability by P. So I think this is satisfied as well, because if we toss a coin, the probability of, for example, the probability of a head is constant. If it's a fair coin, it's going to be equal to 0.5, which is equal to probability of a tail. If it is fair. It is a fair coin. But even though the number two, number three, number four are satisfied, since the number one is not, it's violated. So the first one, the number one, the first example is not a binomial experiment. All right, let's take a look at number two. The number two says that toss a coin 10 times. Now, let's just check the conditions one by one. If the number of trials fixed in advance, I think so, it's 10. So the condition one is satisfied. Number two, how many possible outcomes we have from each toss? Just two, right? Head and tail. So condition two is satisfied. Number three, Are the trials independent? I think so, because whatever we get from the first toast will not affect the result of any other toasts. So number 3 is satisfied. Number 4, same thing. It's gonna be constant probability. If it's a fair coin, the probability of a head is equal to 0.5. Let me rewrite this real quick. It's equal to the probability of tail if it's a fair coin. Okay. Oh, I think there's a misspell here. Oops. So since all of the 4 conditions are satisfied, so number 2 is a binomial experiment. Okay. Now, after number 2, let's take a look at number 3. Toss a fair die 10 times and say if number 1 is tossed or not. Now, let's check the conditions one by one. So the number of trials 10, so it's fixed. So the condition 1 is satisfied. Number 2. So how many possible outcomes do we have here? So it's asking, the problem says toss a fair die 10 times and say if 1 is tossed or not. So what we care about here is if the number we got 1 or not. Okay, we don't have to worry about any other numbers. It could be any other numbers, but we don't care. We don't care. We just care about if it's 1 or not. So there are only 2 possible outcomes. It is number 1, or not number 1. So there are only 2 possible outcomes. So condition 2 is satisfied. Number 3, the independence. I think trials are independent because whatever we get from the first toast will not affect what we get from any other toast. So number 3 is satisfied. Number 4. So now let's see what is the probability that 1 is toast. Of course, we'll assume that this is a fire. Okay, fire die. So, if we assume we're toasting a fair die, the probability that we got a 1 would be 1 over 6. And the probability that not number 1 is 5 over 6. And we know this probability is constant because we assume that it is fair die. So number 4 is satisfied. That which means this is a binomial experiment. So basically, if we want to determine if an experiment is a binomial experiment or not, we just need to check those 4 conditions one by one. If they're all satisfied, then it would be a binomial experiment. Alright, once we know the definition of binomial experiment, let's take a look at the definition of binomial random variable. So the binomial random variable x associated with a binomial experiment consisting of n trials, it will be n trials, is defined as x is equal to the number of success among the n trials. Okay? X represents the number of success among the n trials. Once we know this, let's take a look at the notation here. Because the PMF of binomial random variable x depends on 2 parameters, the number of trials n and the probability of success p, then we denote the PMF by b, little b. X, of course, x is the random variable, and n is the first parameter, which represents the number of trials, and then p represents the probability of success. Okay, so just write it down. P is equal to the probability of success. Okay. Now, let's take a look at this example. Once we know the definition of a binomial random variable, let's take a look at this example here. So this is coming from the number 3 we just went over up here. Toss a fair die 10 times and say if number 1 is tossed or not. What is the probability that x is equal to 3? So actually, there's typo. What is the probability of x is equal to 3? Which means we're looking for probability x is equal to 3. That's what we are looking for. And first of all, let's take a look at the value of the two parameters over here. So what is the value of n? Since we are gonna toast the fair die 10 times, the n would be equal to 10. Okay? And p, the probability p is equal to the probability that 1 is toast. That would be 1 over 6. Then 1 minus p would be equal to the probability that not 1, which is 1 minus 1 over 6 is equal to 5 over 6. Now we're looking for the probability of x is equal to 3. Let's take a look at how to find x is equal to 3. Now we are tossing the die. We're tossing the die 10 times. And we want to find the probability that 3 of them is 1 and 7 of them is not 1. Okay? So the probability get a 1, the probability that 1 is toasted 1 time is 1 over 6. Then what is the probability that the 1 is toasted 3 times? So that would be 1 over 6 to the power of 3. Okay? And then we know 7 of them are not 1. So the probability of each of them is 5 over 6. So the probability of 7 of them would be 5 over 6 divided to the power of 7. Are we done? Not yet. So we need that 10 choose 3 over here. Why? Because we don't know which 3 are the ones and which 7 are not the ones. Okay? It could be the first toast, the second toast, the third toast gave us the ones, and the last 7 toasts are not ones. It could be the first toast, second toast, or the first toast are the ones, and other toasts are not ones. So we're gonna have this amount of different combinations, which is 10 choose 3. Okay, we're gonna choose 3 out of 10 to be the ones, and then the other 7s would be not 1. Okay, so if you type this in your calculator, you will have this approximately equal to 0.155. Okay, so this part, n choose 3 over here is very important, okay, because we're gonna have different combinations. We're gonna have a bunch of different groups will give us 3 ones and 7 of them are not ones. Okay. All right. Once this makes sense to you, and we're gonna talk about the theorem here, the PMF of a binomial distribution, PMF theorem. So of course, the PMF of binomial distribution as the what we just went over here. So if we have x out of n are success, then we're gonna have p to the power of x, because we're gonna have x success, and the probability of that is gonna be p to the power of x. And then we're gonna have n minus x failures. So it's gonna be 1 minus p to the power of n minus x. And then we're gonna have n choose x over here, because we're gonna have a bunch of different groups of successes and failures. Okay, so that's pretty much the same as what we just went over here. X is equal to 3. Of course, in this case, x is 3 and n is 10. P is 1 over 6, x is 3 to the power of 3, and the 1 minus p is 5 over 6 here, and the n minus x, which is 10 minus 3, which is 7. Okay, so if we know this formula, the general form of the PMF of binomial random variable, so we can find, or we can calculate the probability of this x is equal to 3 directly. I think this is pretty straightforward. All right, once this makes sense to you, let's take a look at this example here. So the problem says, this is from the textbook, example 3.31. Each of 6 randomly selected cola drinkers is given a glass containing cola S and one containing cola F. The glasses are identical in appearance except for a code on the bottom to identify the cola. Suppose there is actually no tendency among cola drinkers to prefer one cola to the other. Then the probability little p is representing the probability a selected individual prefers the cola S. And the probability of that is equal to 0.5. So with x is equal to the number among the 6 who prefer S, this random variable follows a binomial distribution with the parameter n is equal to 6 and the p is 0.5. So this is the n, this is the p, right? And then we want to find the probability x is equal to 3. Okay, so if we want to find x is equal to 3, what do we need to do? Just apply the formula. We just get the formula of the PMF of random variable. Okay, n is equal to 6, x is equal to 3. So n is equal to 6, x is equal to 3. So that would be, we're going to have the x here. This is the value of x. So that would be 6 to 3, and then p, which is 0.5 to the power of 3, and then 1 minus p is equal to 0.5 as well. So we have 0.5 here, and then n minus x here is equal to 6 minus 3, which is 3. That's why we have the power of 3 over here. So if you type this in your calculator, you have this probability is 0.313. So I think this is very similar to the one we just went over up here. Okay, so that's how to find the probability of a single point. What do we need to do? Just apply the formula of the PMF of the binomial random variable. And then let's take a look at what is the probability that at least the 3 prefer S. So we're looking for the probability that x is greater than or equal to 3, right? So if x is greater than or equal to 3, which means that x could be 3, 4, 5, and 6. So I'm going to say that the probability x is greater than or equal to 3, that would be equal to the probability of x is equal to 3 plus the probability of x is equal to 4 plus the probability of x is equal to 5 plus the probability of x is equal to 6. And that's it, because the value of n is 6. Okay? And that's what do we get over here. The summation from x is equal to 3 to x is equal to 6, and the PMF here. Okay, and once, of course, this form here is exactly the same thing as what I just put it over here. Okay, so this would be equal to, if we spread it out, I just want to make it clear for you, this would be equal to, when x is equal to 3, that would be 6 to 3, 0.5 to the power of 3 times 0.5 to the power of 3. And then plus, if x is equal to 4, 6 to the 4, and then 0.5 to the power of 4 times 0.5 to the power of 2. And then 6 to the 5. That would be 0.5 to the power of 5, and then 0.5 to the power of 1. And then plus 6 to 6, 0.5 to the power of 6, and then 0.5 to the power of 1. And then you type the whole thing in your calculator, you get the answer is 0.656. And of course, I'm going to show you how to find the probability of interval from the calculator. Okay, I'm going to make a video about that later. Okay, and actually, if we are looking for the probability x is greater than or equal to 3, we can think the opposite of it, okay? Because this would be equal to 1 minus the probability of x is less than or equal to 2. In this case, we're thinking of the complement of the probability of x is greater than or equal to 3. The probability x is greater than or equal to 3 is equal to 1 minus the probability of x is less than or equal to 2. So of course this is equal to 1 minus the summation x is equal to 0 from 0 to 2, and then 6, choose x, and then 0.5 to the power of x, and then 0.5 to the power of 6 minus x. That's another way to think of it, just complement of that. So either way would work, okay? Either this way or this way. Either way would work, okay? Now, what is the probability that at most one prefers x? So if, what does at most one prefers x? That means x is less than or equal to 1, right? If x is less than or equal to 1, that means x could be 0 and x could be 1. So actually this is equal to x is equal to 0, 6 choose 0, and then 0.5 to the power of 0 times 0.5 to the power of 6. And then plus 6 choose 1, 0.5 to the power of 1, 0.5 to the power of 5. And then if you type this whole thing in your calculator, we're going to have the probability is 0.109. Okay? So again, of course, we are able to find this kind of probability from the calculator. And I'm going to make a video later on. Okay, once this is clear, based on what we went over before, 3.2 or 3.1, and we also talking about the idea of a CDF, cumulative distribution function, CDF, and we know that the CDF is equal to the probability that x is less than or equal to the little x. That means that would be equal to the sum of all probabilities y is equal to 0 from x, from 0 to x. Okay, this is pretty much the same idea as what we went over in 3.2. Actually, there is a special case. If n is equal to 1, the binomial distribution becomes the Bernoulli distribution. Why? Because we know that if a random variable is a Bernoulli random variable, that means the possible outcome of this kind of random variable only 2, success and failure. And if n is equal to 1, that means the number of choices is 1. That means we only conduct the experiment one time. And this experiment only has 2 possible outcomes. Then we call it Bernoulli random variable. Of course, the distribution of it is called Bernoulli distribution. That's just a special case. Okay? All right. If there's a proposition, if we have the random variable x follows a binomial distribution with the parameter n and p, then the expected value of x is equal to n times p, and the variance is equal to np times 1 minus p. And the standard deviation is going to be equal to the square root of variance, which is equal to the square root of npq, of course, where q is equal to 1 minus p, okay? So this proposition is very important. Once you know this proposition, it's going to be save you a lot of time to calculate the variance and the expected value of a binomial probability distribution. Now, let's take a look at this example. So if 75% of all purchases at a certain store are made with a credit card, and x is a number among 10 randomly selected purchases made with a credit card, then in this case, x follows binomial distribution because there are only 2 possible outcomes. One is the purchase made with a credit card, or the purchase not made with a credit card. So there are only 2 possible outcomes, and this is a binomial distribution. And n is equal to 10. N is equal to 10. And then p is equal to 0.75. So we say that x follows a binomial distribution with n is equal to 10, p is equal to 0.75. Now, I want to find the expected value of x. So we can just figure it out directly based on the proposition we have here. The expected value of x is equal to np, which is n times 0.75, which is 7.5. And then what is the variance? Variance is equal to MPQ, which is N is 10, P is 0.75, Q is 1 minus 0.75, right? And this is equal to 1.875. And then what is the standard deviation? Of course, standard deviation is equal to the variance of the square root of variance, which is square root of 1.875, which is equal to, approximately 1.37. So that's pretty much how to apply the this proposition here, and this is very important. All right, that's pretty much all about the binomial probability distribution. And then in 3.5, since 3.5 is not the most important thing, so I wouldn't talk too much about it in the lecture videos. And this section would be a reading practice, and I'm gonna skip it in the lecture video. And in next video, we're gonna talk about 3.6 directly. Okay, we're gonna get into 3.6 directly and skip 3.5. And if you are interested in it, I encourage you to read the section 3.5 by yourself after class. All right, that's pretty much all about this video.